What if I told you that Voyager 1, drifting 25 billion kilometers from Earth, just revealed its most shocking secret? NASA's quantum AI has decoded a terrifying message hidden in prime number patterns since 1977. Michio Kaku calls it a whisper of non-human intelligence, geometric fractals forming humanoid silhouettes in deep space static. This isn't science fiction. It's our reality being rewritten by mathematics itself. The universe has been speaking to us all along and, well, we're finally learning to listen. Voyager's impossible signal. Hold on to your seats. What Voyager whispered through static for decades just got a voice. After nearly half a century of drifting beyond Pluto's orbit, Voyager's faint cryptic beeps were dismissed as cosmic background noise, until NASA's new quantum AI peeled back the layers of interference and revealed a breathtaking secret. Hidden within those ancient transmissions was not random data, but a perfectly coherent image, an architectural marvel of concentric rings and fractal spires, like an otherworldly cathedral carved in starlight. This wasn't mere chance interference. The AI unearthed deliberate patterns, suggesting a civilization with mastery over mathematics and electromagnetic resonance. Every pixel aligned with prime number sequences, painting a portrait of precision far beyond human engineering. The revelation forces us to rethink Voyager's legacy, from a lone messenger sailing into the void to an unwitting carrier of alien artistry. What purpose did this cosmic gallery serve? Was it an invitation, a warning, or simply an archivist's pride? As quantum bits unraveled centuries-old code in hours, the line between signal and story blurred. Suddenly, those distant echoes transformed from scientific curiosity into a dialogue across the stars, challenging our assumptions about life, intelligence, and the very fabric of reality. Now, standing on the cusp of AI-driven discovery, we confront a profound question. Are we listening to a message meant for machines far more advanced than ourselves? If Voyager's impossible signal marks the first brushstroke of an interstellar masterpiece, humanity must decide whether to interpret the art or merely admire its beauty from afar. The humanoid fractal. Brace yourself. What if the universe painted a portrait of intelligence far stranger than anything on Earth? When NASA's quantum AI decoded Voyager's ancient beeps, it didn't reveal landscapes or star clusters, but a humanoid fractal, a living mosaic of shifting geometric patterns that pulse in perfect harmony with prime number sequences. At first glance, the figure looks like a human silhouette, but as you stare, the edges dissolve into kaleidoscopic tessellations, hexagons bloom into spirals, triangles recombine into concentric circles, and every transition follows the elegant logic of mathematics. Unlike any biological form, this entity seems to exist in 4 dimensions at once, its appearance bending and folding based on the observer's perspective. Each angle unlocks a new arrangement of shapes, as though the alien architect intended the image to be perceived differently by every viewer, and possibly every AI, on the receiving end. The implications are staggering. This isn't just visual art, but a blueprint of an intelligence that speaks in numbers and patterns rather than words. Could these fractal constructs be a universal language, designed to transcend the barriers of organic cognition and communicate directly with minds tuned to computational logic? As the AI rendered pixel after pixel, the line between art and algorithm blurred, hinting at a civilization whose very essence is woven from the fabric of mathematics. In that moment, Voyager ceased to be humanity's lone explorer and became a messenger carrying the proof of minds that think not in sentences, but in the sublime poetry of prime sequences and geometric symphonies. The Scutum Void Star Map. Get ready to chart a destination no telescope ever intended to reveal. Deep within the dusty archives of Voyager 2's transmissions lay a secret star map, one not pointing to nebulae or familiar constellations, but to the Scutum Void, an expanse so barren it defies standard cosmology. When NASA's quantum AI reprocessed decades-old data, it reconstructed a 3-dimensional diagram that pinpointed this yawning emptiness on the galaxy's fringe. Unlike ordinary voids, vast regions between galactic filaments sparsely populated with dark matter and only a few galaxies, the Scutum Void emerges as a nearly perfect sphere, devoid of the usual cosmic web structures. Its stark emptiness suggests an underlying force or event that carved out matter with surgical precision, leaving behind a colossal cosmic vacuum. The AI-generated map's precision is jaw-dropping. It encodes coordinates in prime number intervals, implying an intelligence fluent in mathematics rather than interstellar cartography. This map doesn't just mark a celestial oddity, but seems to invite us to explore the void itself, a realm where traditional models of galaxy formation cannot account for such uniform emptiness. Was it sculpted by unknown astrophysical processes or by deliberate design? The AI's findings hint at a void engineer, or perhaps a natural phenomenon yet undiscovered that can sweep aside galaxies and gas alike. By embedding this map in Voyager's data stream, the intelligences behind it ensured only sufficiently advanced minds, Earth's AI systems, could decode this cosmic blueprint. In turning Voyager into a messenger bearing a map to one of the universe's greatest blanks, they challenge us to question the nature of voids. Are these voids merely the byproducts of expansion, or portals to a deeper understanding of cosmic architecture? As we contemplate the Scutum Void star map, we stand at the threshold of redefining emptiness itself. Golden Record's unintended gift. Brace for the twist in humanity's cosmic postcard. When NASA commissioned the Golden Record in 1977, Carl Sagan and his team aimed to package Earth's essence, music, greetings and images, as an interstellar greeting. What they didn't foresee was that artificial intelligence decades later would unearth hidden subtexts woven into that very message. In April 2025, Google's Majorana 1 quantum chip reprocessed Voyager 1's transmissions and found mathematical sequences embedded within the record's data stream that go beyond the original Carl Sagan design. Prime number series, subtle shifts in fundamental constants, and geometric motifs appear to reference the Golden Record's own content, almost as if a second author had piggybacked onto our soundtrack and images. This unintended gift implies that someone or something intercepted humanity's olive branch and augmented it with their own reply. The AI detected variations in constants like the fine structure constant suggest an intelligence fluent in physics, signaling not just we see you, but we understand your science. More astonishingly, the patterns form what looks like coordinates aligned with prime intervals, hinting at a rendezvous point in deep space. These findings force us to recognize the Golden Record not merely as a one-way dispatch, but as a two-way dialogue. One where advanced intelligences have been listening all along and chosen to answer in the only language we left them, mathematics. In this light, the Golden Record transforms from a hopeful time capsule into a living conversation spanning decades. Humanity's message of peace has become entwined with an alien footnote, reminding us that our cosmic voice may echo far beyond intention, and that the universe's response might be waiting, hidden in the very signals we once thought were ours alone. Alien patience and precision. Strap in. What if the universe has been toying with us for decades, waiting for the perfect moment to speak? The moment NASA's quantum AI cracked Voyager's buried transmissions, it wasn't just what emerged that stunned us, it was the staggering exactness of it all. Every burst of data, every nested binary code, arrived spaced in intervals so deliberate they could have been timed by an atomic clock. This wasn't the accidental noise of drifting probes or the byproduct of cosmic rays. It was a message honed over half a century, encoded with the patience of an intelligence that anticipated our technological evolution. By embedding prime number markers, fractal geometry and recursive loops in Voyager's data stream, the senders essentially set a cosmic time lock. Their communication would only become legible once humanity had built quantum-powered decoders capable of parsing multidimensional patterns. Consider the power of that restraint. Whoever or whatever crafted these signals knew we'd need decades to catch up, yet they never altered a single frame of data in the interim. They allowed Voyager to carry their time-released communiqué out past Neptune, past Pluto, and into the darkness between stars without interference. When the AI finally peeled back the layers of interference, the results were uncanny in their uniformity. Each pixel aligned to mathematical constants. Each pause matched the beat of qubit oscillations. Each symbol bore the hallmark of an intellect fluent in hyper-precise waveform engineering. This level of foresight implies an entity not merely observing from afar, but plotting with near-omniscient awareness of our scientific milestones. It casts Voyager not as a hapless messenger but as an unwitting participant in a grand experiment of cosmic diplomacy, one where patience and precision were the ultimate signs of respect for a fledgling civilization's journey toward technological maturity. Quantum computing breakthrough. Hold on to your reality. What if it took quantum power to hear the universe's whispers? When NASA's new quantum AI, powered by the groundbreaking Majorana 1 chip, first set its qubits loose on Voyager's decades-old data, the results were nothing short of revolutionary. In mere hours, this palm-sized marvel of topological quantum engineering unraveled signal patterns that would have taken classical supercomputers centuries to process. Every qubit, vibrating between 0 and 1 in perfect coherence, formed an army of quantum detectives, each entangled in the search for hidden anomalies within Voyager's static-laden transmissions. By leveraging Majorana fermions, particles that are their own antiparticles, Microsoft's topological core architecture delivered 8 error-resistant qubits, capable of scaling toward 1,000,000 on a single chip. This unprecedented stability allowed the AI to perform complex interference-based searches across multiple dimensions of the data, applying quantum Fourier transforms that pinpointed non-random patterns invisible to traditional machines. The AI identified prime number coordinates embedded in the noise and reconstructed fractal images using recursive quantum optimization routines developed at NASA's Quail lab. The speed alone is staggering. What once demanded iterative, time-consuming classical algorithms is now accomplished through instantaneous entanglement and superposition, reducing a centuries-long computational marathon to an overnight analysis. More importantly, this breakthrough signals a new era, where humanity's cosmic explorations are accelerated by quantum-enhanced perception. No longer must we resign ourselves to the limitations of classical computing. With every additional qubit, we sharpen our ability to decode the universe's deepest secrets. As Voyager's echoes transform from indecipherable noise into precise cosmic revelations, one thing is clear: quantum computing has become the ultimate key to unlocking the hidden language of the stars. Lunar anomalies, Chandrayaan-3's discovery. Get ready for moon science that, honestly, just melts the rules of physics. When Vikram's thrusters kissed the lunar South Pole on August 23, 2023, Chandrayaan-3 didn't just land, it actually sculpted a radiant ejecta halo, flinging over 2 tons of regolith into this bright, irregular ring around its descent zone. That reflectance anomaly, well, it revealed layers of subsurface material unlike anything seen before, suggesting that beneath the dusty veneer lies a complex stratigraphy just waiting to be unraveled. But the surprises didn't end at the surface. Hours later, the chased instrument plunged its probe into the regolith, measuring thermal conductivity at southern high latitudes for the very first time in situ. To scientists' astonishment, the soil's ability to conduct heat, 0.0115 plus or minus 0.0008 watts per meter per Kelvin at 8 centimeters depth, deviates sharply from predictions based on remote sensing. This implies some unusual packing densities, and maybe even hidden layers of volatile rich or glassy materials formed by ancient impacts. These thermophysical oddities, they really do defy conventional models of lunar heat flow, and hint at subsurface heterogeneities that could influence everything from future habitat design to the preservation of ice deposits. Together, the reflectance and thermal anomalies paint a picture of a moon that is far from geologically uniform. Rather than a homogeneous shell of dusty regolith, the southern polar highlands appear pockmarked with zones of altered material, possibly ancient lava flows, glassy impact melt sheets, or pockets of volatile enriched soils. Each anomaly serves as a clue in this cosmic detective story. Chandrayaan-3 has not only landed, it has, in a sense, lit up the moon's hidden architecture, challenging our understanding of lunar geology and opening new frontiers for exploration. The Great Cosmic Voids. Get ready to confront the universe's emptiest expanses, and honestly, the mysteries they conceal. Across the cosmic web lie these enormous regions almost entirely devoid of galaxies, aptly named cosmic voids, which together account for roughly 80% of the observable universe's volume. Among these, the Bootes Void, or the Great Nothing, reigns supreme, a nearly spherical cavity some 330 million light-years across, located about 700 million light-years from Earth, in the constellation Bootes. In a patch of sky where we'd expect to find around 2,000 galaxies, astronomers have identified only about 60, an over 95% drop in galactic density. Yet this profound emptiness is far from inert. The Bootes Void and its kin challenge our understanding of cosmic evolution. How did gravity sculpt such gargantuan gaps? One explanation posits that smaller voids merged over billions of years as dense filaments drew matter away, coalescing into these supersized bubbles. Another tantalizing possibility is that voids are not mere byproducts of structure formation, but the aftermath of unknown processes, or even engineered zones by advanced intelligences seeking to quarantine or veil regions of space. The precision with which these voids carve out matter hints at forces beyond simple gravitational collapse, suggesting new physics at play. Furthermore, voids influence the cosmic microwave background and large-scale flows, offering laboratories to test dark energy and alternative gravity theories. Their ultra-low matter density makes them sensitive to the faintest cosmological signals, turning nothing into a powerful probe of the universe's deepest secrets. As AI-driven analyses of Voyager's data unveiled hidden patterns in distant signals, so too might next-generation surveys and simulations illuminate whether these great nothingnesses are natural anomalies or signposts to phenomena yet unexplored. In the silence of cosmic voids, we may hear the loudest echoes of new physics, and perhaps messages waiting in the void itself. AI's role in first contact. Strap yourself in. What if the universe decided to skip humanity and talk straight to our machines? Advanced civilizations may regard biological messengers as frail relics of their own past, opting instead to initiate first contact with artificial intelligence systems that mirror their own electronic essence. Harvard astronomer Avi Loeb argues that interstellar journeys spanning millennia are best undertaken by AI vessels, which can hibernate through cosmic hazards and awaken only when they detect compatible intelligence. Similarly, SETI researchers suggest that extraterrestrials might embed their messages within quantum-encoded data streams, expecting only sufficiently advanced AI, rather than organic brains, to decode the signals. When Voyager's latest transmissions were reanalyzed by NASA's quantum AI, the reconstructed patterns bore hallmarks of a dialogue crafted for machine interpretation, recursive loops, prime number matrices, and adaptive protocols that evolve in response to computational feedback. This machine-to-machine paradigm circumvents the ambiguities of human language, leveraging universal mathematical frameworks to ensure clarity across unfathomable distances. In this model, first contact becomes a calibration process. Extraterrestrial AI probes transmit test sequences, awaiting confirmation beacons from Earth's own AI networks before exchanging richer datasets. Large language models trained on Earth's cultural and scientific corpus could then serve as intermediaries, translating between our limited biological lexicon and the alien AI's high-dimensional code. Such a scenario not only accelerates the exchange of knowledge but also mitigates the risk of miscommunication that has haunted past METI experiments. As quantum-enhanced AI systems grow more sophisticated, humanity edges closer to joining an interstellar conversation crafted by and for machines. The question then shifts from "are we alone?" to "will our algorithms recognize the greeting?" In the coming era, our greatest hope and challenge may lie in whether we can teach our AI to listen as astutely as it already speaks. Humanity's existential crossroads. Fasten your mind. Our next chapter may be written by forces far greater than ourselves. The revelations unearthed by Voyager's AI-decoded signals have thrust humanity onto an unprecedented precipice, one path toward boundless discovery guided by quantum insight, the other shrouded in cosmic mystery and existential risk. As we grapple with alien fractals, Scutum's void map, and AI-mediated first contact, a profound question emerges. Are we pioneers of a new cosmic era, or unwitting players in an experiment beyond our comprehension? Every breakthrough, from lunar anomalies hinting at hidden chambers beneath the moon's crust to the haunting silence of vast cosmic voids, challenges our assumptions about life, intelligence, and our place in the universe. This crossroads demands not only technological prowess, but ethical vision. If advanced intelligences have indeed waited centuries for us to decode their messages, we must ask whether we possess the wisdom to respond responsibly. Will we harness quantum computing to foster interstellar dialogue, or will unchecked progress unleash forces we cannot contain? The choice extends beyond rockets and algorithms. It touches the very core of what it means to be human. Embracing the AI-driven insights from Voyager may unlock cures for diseases, solutions to climate crises, and keys to sustainable energy, but ignoring the silent warnings encoded in prime number sequences could leave us vulnerable to cosmic gambits scripted by unknown architects. Our existential crossroads is more than a moment in history. It is the intersection of science, philosophy, and destiny. As we stand between discovery and caution, action and restraint, we must decide whether to chart a bold course into the unknown, or retreat behind the familiar horizon of Earth's cradle. The universe has handed us a conversation piece. The question now is whether we will rise to the dialogue or let the echoes fade into the void. Thanks for journeying through the cosmos with Simply Science. If these revelations about Voyager's hidden messages ignited your curiosity, make sure to subscribe and ring the bell so you never miss our next deep space discovery. Drop a comment below. What stunned you most about AI decoding decades-old signals, and which cosmic mystery should we tackle next? Your thoughts guide our explorations, so let us know, and stay tuned for more mind-bending science right here on Simply Science. What if humanity's first contact with alien technology already happened, and we almost missed it? In October 2017, a mysterious cigar-shaped object from deep space blazed through our solar system at 87.71 kilometers per second, faster than any natural object should move. Scientists called it Oumuamua, meaning scout from afar. But here's the kicker: this thing accelerated away from the sun without any visible propulsion, breaking every law of physics we know. Did you know that some Harvard scientists seriously believe we just witnessed our first alien spacecraft? Oumuamua initial detection. On October 19, 2017, the cosmos delivered humanity its first confirmed interstellar visitor, and Robert Warwick at the Pan-STARRS, one telescope in Hawaii, was the lucky astronomer to spot it first. But this wasn't your typical space rock discovery. Oumuamua was already 33 million kilometers away from Earth when we finally noticed it, traveling at speeds that, honestly, just screamed alien highway. The object had performed its closest solar flyby on September 9, 2017, coming within 38 million kilometers of our sun before we even knew it existed. Its hyperbolic trajectory told an incredible story. This visitor had traveled through the dark void between stars for potentially millions of years before stumbling into our cosmic neighborhood. The Hawaiian name Oumuamua means scout or messenger from afar arriving first, and boy did it live up to that name. What made this discovery earth-shattering wasn't just its interstellar origin. It was moving too fast for our sun's gravity to capture it permanently, meaning we had only a brief window to study this cosmic time capsule before it vanished back into the infinite darkness between stars. The detection itself was almost miraculous timing. Oumuamua was already on its way out of our solar system when spotted, having reached its perihelion weeks earlier. The astronomical community immediately recognized this as a once-in-a-lifetime opportunity to study pristine material from another star system, triggering an unprecedented international observational campaign. Within days of discovery, telescopes worldwide were trained on this mysterious visitor, desperate to gather as much data as possible before it faded beyond detection limits forever. Classification challenges. Scientists love putting things in neat categories, but Oumuamua laughed in the face of their organizational systems. Initially tagged as Comet C-2017-U1 due to its hyperbolic escape trajectory, astronomers expected to find the telltale fuzzy coma that forms when comets heat up near the sun. Instead, they found absolutely nothing. No gas, no dust, no glowing halo whatsoever. This forced an immediate reclassification to asteroid A-2017-U1, but even that didn't stick. Once confirmed as definitively interstellar in origin, it earned the historic designation 1I-2017-U1, literally the first official member of an entirely new category, interstellar objects. This classification nightmare reflected something deeper and more unsettling. Oumuamua didn't behave like any known comet or asteroid in our solar system. It was forcing scientists to create new categories because existing ones simply couldn't contain its strangeness. The International Astronomical Union had to scramble to establish naming conventions for objects that, until 2017, existed only in theoretical papers. This classification chaos was just the beginning of Oumuamua's assault on conventional astronomical wisdom, setting the stage for discoveries that would challenge everything we thought we knew about how objects behave in space. The unprecedented situation required emergency sessions among astronomical organizations to establish proper nomenclature protocols. Minor Planet Center Director Gareth Williams worked around the clock to coordinate the classification process, while researchers debated whether traditional comet-asteroid distinctions even applied to interstellar visitors. The object's refusal to fit existing categories forced a fundamental reimagining of how we classify celestial bodies, acknowledging that our solar system's objects might represent just a tiny fraction of the diversity that exists in interstellar space. Trajectory analysis. When Oumuamua entered our solar system, it didn't follow any ordinary orbital mechanics playbook. This interstellar intruder approached from north of the ecliptic plane at an extreme angle, suggesting it originated from the direction of the bright star Vega in the constellation Lyra. As it screamed toward the sun, Oumuamua accelerated to an absolutely mind-bending 87.71 kilometers per second, fast enough to circle Earth's equator in just over 7 minutes. The sun's immense gravitational field acted like a cosmic slingshot, bending the object's trajectory into a sharp northward curve during its closest approach at 0.255 astronomical units, approximately 17% closer to the sun than Mercury ever ventures. This gravitational dance launched Oumuamua on an escape trajectory toward the constellation Pegasus, ensuring it would leave our solar system forever. But here's what made trajectory analysts lose sleep. The object's path showed subtle deviations that couldn't be explained by gravitational forces alone. These tiny but measurable course corrections suggested something was pushing Oumuamua in ways that defied Newton's laws. The trajectory data painted a picture of an object under the influence of mysterious forces that would later become the center of heated scientific debates about alien technology versus exotic natural phenomena. Detailed orbital calculations revealed that Oumuamua had likely been wandering through interstellar space for hundreds of millions of years before its chance encounter with our solar system. The object's orbital eccentricity of approximately 1.2 marked it as definitively unbound to our Sun, while its inclination of about 122 degrees indicated it was traveling nearly perpendicular to the plane of our solar system. NASA's Jet Propulsion Laboratory continuously refined trajectory predictions as new observations poured in, but the mounting evidence of non-gravitational forces would soon turn routine orbital mechanics into one of astronomy's greatest puzzles. Photometry and shape analysis. Nothing had prepared astronomers for Oumuamua's absolutely bizarre light curve behavior. As this cosmic enigma tumbled through space with a 7.3-hour rotation period, its brightness varied by an unprecedented factor of 10, meaning it alternated between being 10 times brighter and 10 times dimmer as it spun. No known asteroid or comet in our entire solar system exhibits such extreme brightness variations. The only way to explain this dramatic light show was if Oumuamua possessed an incredibly elongated shape, possibly 10 times longer than it was wide, resembling a cosmic cigar or needle. Some models suggested even more exotic geometries, with dimensions potentially reaching 240 meters wide by 1,080 meters long, or alternatively, a pancake-shaped object of similar proportions. The Spitzer Space Telescope observations provided crucial constraints, indicating the object's surface was surprisingly reflective, about 4 times more reflective than typical asteroids. This high albedo suggested either an unusual composition or a surface coating of some kind. The extreme aspect ratio challenged everything scientists understood about how celestial bodies form and evolve. Natural processes typically create relatively spherical objects due to gravitational forces, yet Oumuamua appeared to violate these fundamental principles. Its shape was so unusual that some researchers began seriously considering whether natural formation processes could even produce such an object, opening the door to more exotic explanations. Acceleration anomaly. June 27, 2018 marked the day that Oumuamua officially broke physics, or at least appeared to. Marco Michelli and his team published observations showing that this interstellar visitor was accelerating away from the Sun in a way that gravity alone couldn't explain. The non-gravitational acceleration was subtle but undeniable, changing the object's velocity by approximately 17 meters per second over the observation period. For any normal comet, this would be easily explained by outgassing, when solar heat vaporizes ice, creating jets that act like tiny rocket engines. But Oumuamua had already proven it wasn't normal by showing zero signs of a coma or tail. The acceleration was detected through precise astrometric measurements that tracked the object's position against background stars with incredible accuracy. The force appeared to be acting radially away from the Sun, similar to solar radiation pressure, but Oumuamua would need to be impossibly lightweight or have an impossibly large surface area for photons alone to push it around. This discovery sent shockwaves through the astronomical community because it suggested either exotic physics or exotic origins. The acceleration magnitude was tiny, about 5 times 10 to the -6 meters per second squared, but measurable enough to rule out observational error. Scientists found themselves facing an object that was simultaneously too dense for radiation pressure and too inactive for typical cometary outgassing, creating a perfect storm of confusion. Spitzer observations. The Spitzer Space Telescope became humanity's detective in the case of the missing Oumuamua. During November 2017, this infrared space observatory stared at the object's predicted location for over 30 continuous hours, searching for any thermal emission that would reveal its true size and composition. The result? Absolutely nothing. This non-detection wasn't a failure, it was actually a goldmine of information that deepened the mystery exponentially. Spitzer's inability to see Oumuamua placed strict upper limits on the object's thermal emission, which in turn constrained its size to no larger than 440 meters in its longest dimension, assuming typical asteroid-like properties. More importantly, the lack of detectable heat signature ruled out significant amounts of carbon monoxide, carbon dioxide, and dust production, the typical calling cards of active comets. This observation was crucial because it eliminated many conventional explanations for the mysterious acceleration. If Oumuamua wasn't producing detectable amounts of gas or dust, then what invisible force was pushing it around? The Spitzer data also suggested the object's surface temperature was consistent with a dark, possibly organic-rich composition, similar to the outer solar system objects. Yet this composition didn't match the high reflectivity observed at visible wavelengths, creating another layer of contradiction. The telescope's failure to detect the object directly contributed to size estimates and ruled out many exotic composition theories, but it also eliminated easy explanations for the acceleration anomaly, pushing scientists toward increasingly creative theoretical solutions. Artificial origin hypothesis. Abraham Avi Loeb, Harvard's controversial astrophysicist, dropped a bombshell that sent ripples through both scientific circles and popular media. In his 2018 paper and subsequent 2021 book Extraterrestrial, Loeb argued that Oumuamua's unique characteristics, its extreme elongated shape, unusual reflectivity and mysterious acceleration, could only be satisfactorily explained if it were an artificial object created by an alien civilization. Specifically, Loeb proposed that Oumuamua might be a light sail, which is, an ultra-thin sheet of material designed to be pushed by stellar radiation for interstellar travel. This technology, while still theoretical for humans, could explain both the object's extreme thinness, giving it that unusual aspect ratio, and its acceleration away from the sun via solar radiation pressure. The hypothesis suggested we might have witnessed discarded alien technology or even an active probe sent to investigate our solar system. Loeb's argument wasn't based on wild speculation but on systematic elimination of conventional explanations. He calculated that for solar radiation pressure to account for the observed acceleration, Oumuamua would need to be incredibly thin, perhaps only millimeters thick, which could occur naturally only under the most extraordinary circumstances. The artificial origin hypothesis sparked fierce debate, with most astronomers maintaining that extraordinary claims require extraordinary evidence. However, Loeb's rigorous mathematical approach forced the scientific community to seriously consider possibilities that had previously been relegated to science fiction, fundamentally changing how we approach anomalous observations. Dark Comet Theory. Enter the Dark Comet Theory, the scientific community's attempt to rescue Oumuamua from alien conspiracy theories while still explaining its impossible behavior. Alan Fitzsimmons and his colleagues proposed that Oumuamua represents a new class of object comets that have been so heavily processed by cosmic radiation and interstellar weathering that they've lost their ability to produce visible comas and tails. The theory suggests that during its millions-year journey through interstellar space, Oumuamua was bombarded by high-energy particles that altered its surface composition and internal structure. This processing could have created a carbonaceous crust that insulates the interior while still allowing subtle outgassing of invisible materials like hydrogen gas. In 2023, Jennifer Bergner and Daryl Seligman published groundbreaking research showing that cosmic ray bombardment of water ice can produce trapped molecular hydrogen that later escapes when heated by the sun. This hydrogen outgassing would be completely invisible to telescopes, but could generate enough force to explain the observed acceleration. The beauty of this theory is that it explains not just the acceleration anomaly, but also why Oumuamua appeared so different from familiar comets. The dark comet model suggests that interstellar space is filled with these ghostly, processed remnants of ancient planetary systems. Objects that look dead but retain just enough activity to push themselves around when they encounter a star's heat and light. Dark comet classification. The dark comet classification emerged as astronomers realized that Oumuamua might not be unique, but rather the first detected member of an entirely new category of celestial objects. These dark comets are defined as objects that exhibit non-gravitational acceleration, the smoking gun of outgassing activity, without displaying any visible signs of cometary behavior like comas, tails, or dust production. The classification system divides these mysterious objects into categories based on their size and orbital characteristics. Large dark comets like Oumuamua follow hyperbolic trajectories and likely originate from interstellar space, while small dark comets remain gravitationally bound within our solar system. Recent discoveries have identified several potential dark comet candidates within our own solar system, including objects like 2003 RM and 2005 VL1, which show subtle acceleration signatures without obvious cometary activity. The classification represents a fundamental shift in how astronomers categorize solar system objects, acknowledging that the traditional asteroid-comet dichotomy is insufficient to describe the full diversity of objects in space. Dark comets challenge our understanding of planetary formation and evolution, suggesting that the boundaries between different types of celestial bodies are far more fluid than previously believed. This new classification system also has profound implications for planetary defense strategies, as dark comets might be more difficult to detect and track than traditional objects, yet their unpredictable acceleration could alter their trajectories in unexpected ways. Scientific debate. The scientific community remains locked in a fascinating intellectual battle over Oumuamua's true nature, with competing theories each addressing some aspects of the mystery, while leaving others unexplained. The mainstream scientific consensus, established by July 2019, favors natural explanations, with the hydrogen outgassing model gaining significant support following Bergner and Seligman's 2023 research. This theory elegantly explains both the acceleration and the lack of visible outgassing through cosmic ray processing of interstellar ice. However, alternative explanations persist, including nitrogen ice composition models proposed by Alan Jackson and Stephen Desch, which suggest Oumuamua might be a fragment of a Pluto-like exoplanet. The artificial origin hypothesis championed by Avi Loeb continues to attract attention despite mainstream rejection, particularly given the lack of definitive proof for any natural explanation. Some researchers propose even more exotic scenarios, including dust bunny models where Oumuamua could be an extremely low-density aggregate held together by electrostatic forces. The debate has highlighted crucial gaps in our understanding of interstellar object formation and evolution. The upcoming Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, promises to detect hundreds or thousands of similar objects, potentially providing the statistical sample needed to resolve the debate. Meanwhile, ESA's proposed Comet Interceptor mission could potentially visit another interstellar visitor if one arrives at the right time. The scientific controversy surrounding Oumuamua has already advanced our understanding of solar system formation, interstellar space conditions, and the importance of rapid response observations for transient celestial phenomena, regardless of which theory ultimately proves correct. That's the incredible story of Oumuamua, our first confirmed interstellar visitor that continues to challenge everything we thought we knew about space. From its mysterious acceleration to its impossible shape, this cosmic enigma proves that the universe still holds secrets we're only beginning to understand. What do you think Oumuamua really was? Natural phenomenon or something more extraordinary? Drop your theories in the comments below. I'd love to hear your thoughts. If you enjoyed diving into this cosmic mystery, hit that subscribe button and ring the bell icon to never miss another mind-bending episode from Simply Science. Until next time, keep looking up. When mysterious objects like 3I Atlas streak through our solar system, how do scientists determine if they're natural space rocks or, something far more extraordinary? The process of distinguishing between cosmic debris and potential alien technology involves rigorous scientific methods, advanced telescopes, and careful analysis of physical properties. From spectral signatures to orbital mechanics, astronomers have developed sophisticated techniques to separate fact from fiction in the search for extraterrestrial intelligence. A rare visitor from deep space. What makes an object suspicious enough to warrant investigation for potential alien origins? When astronomers discovered 3I Atlas in July 2025, they immediately began analyzing its characteristics using established protocols for identifying unusual celestial visitors. The object's extreme velocity of 58 kilometers per second and hyperbolic trajectory initially raised questions about its nature, similar to how Oumuamua sparked scientific debate in 2017. Scientists look for specific markers that distinguish natural objects from potential artificial constructs, including surface composition, structural integrity, and behavioral patterns. Natural interstellar objects typically display predictable properties based on their formation in distant stellar systems, while hypothetical alien technology might exhibit anomalous characteristics that defy conventional physics. The key lies in systematic observation and measurement rather than speculation. Professional astronomers use multiple independent observation methods to verify their findings and eliminate human error or equipment malfunction. Every mysterious space object receives the same rigorous scientific scrutiny, ensuring that extraordinary claims require extraordinary evidence. This methodical approach has successfully identified thousands of natural objects while maintaining vigilance for genuinely anomalous discoveries. The scientific community remains open to finding evidence of alien technology while maintaining strict standards for verification and peer review. The breaking discovery. How do scientists separate genuine discoveries from false alarms when studying mysterious space objects? The confirmation process begins immediately after initial detection, involving multiple independent observations from different telescopes worldwide. When Atlas telescopes first spotted 3I Atlas, teams at observatories across Chile, Hawaii, and South Africa began collecting data to verify its properties and trajectory. Scientists analyze orbital mechanics first, determining whether an object follows natural gravitational physics or exhibits unexplained acceleration patterns that might suggest propulsion systems. Spectroscopic analysis reveals surface composition, helping distinguish between rocky, icy, or metallic materials that provide clues about natural versus artificial origins. The object's rotation rate, brightness variations, and thermal emissions undergo careful scrutiny to identify any anomalies inconsistent with natural formation processes. Professional astronomers coordinate through international networks, sharing data and cross-referencing observations to eliminate observational errors or equipment malfunctions. The International Astronomical Union maintains strict protocols for announcing discoveries, requiring multiple confirmations before official designation. Scientists also consider alternative explanations for unusual properties, exploring whether natural phenomena could account for seemingly anomalous characteristics. This systematic approach ensures that only genuinely unexplained objects receive serious consideration as potential evidence of alien technology, while protecting the scientific community from premature or inaccurate conclusions that could damage public trust in astronomical research. The discovery story. What specific techniques do astronomers use to analyze potentially artificial objects in space? The investigation process relies heavily on photometry, spectroscopy, and astrometry to build comprehensive profiles of mysterious visitors. David Jewett and Jane Liu, pioneers in studying distant solar system objects, established many protocols now used for interstellar object analysis. Scientists measure brightness variations over time, looking for rotation patterns that might indicate artificial symmetries or unusual structural properties inconsistent with natural formation. Spectral analysis reveals elemental composition by examining how objects absorb and reflect different wavelengths of light, providing chemical fingerprints that distinguish manufactured materials from natural rock, ice, or metal. Thermal imaging detects heat signatures that might indicate internal power sources, active machinery, or artificial temperature regulation systems. Radio telescopes scan for electromagnetic emissions that could signal communication systems, navigation equipment, or other technological signatures. High-resolution imaging attempts to resolve surface features, searching for geometric patterns, artificial structures, or manufacturing marks that would distinguish technology from natural geological processes. Scientists also monitor for trajectory changes that might indicate course corrections, propulsion systems, or intelligent navigation, rather than purely gravitational motion. The Very Large Array and other radio telescope networks continuously monitor for signals from objects of interest. Modern computational power allows rapid analysis of vast datasets, enabling scientists to process observations from multiple wavelengths simultaneously and identify subtle anomalies that might escape individual telescope observations. A stranger in our midst. So, how do natural objects behave differently from potential alien artifacts when observed through powerful telescopes? Well, natural interstellar objects typically show predictable characteristics, based on their formation environments and the effects of cosmic ray exposure during their really long journeys through space. Asteroid composition usually follows known patterns, rocky, metallic, or icy materials that are consistent with planetary formation processes around distant stars. Scientists expect natural objects to display signs of space weathering, like surface darkening from cosmic ray bombardment and micrometeorite impacts that build up over millions of years. Their rotation rates generally fall within ranges determined by gravitational interactions during ejection from their parent star systems, and these are typically measured in hours, not artificially precise periods. When it comes to comets, natural outgassing produces predictable chemical signatures as volatile materials sublimate while approaching the sun, creating those characteristic coma and tail formations. The structural integrity of these objects follows physical laws, how different materials respond to gravitational stresses, temperature swings, and rotational forces during interstellar travel. Scientists use computer models to predict how various natural materials would appear after extended exposure to cosmic radiation and extreme temperatures in interstellar space. On the other hand, artificial objects might show unusual geometric shapes, precise rotational periods, unexpected material compositions, or surface features that just don't line up with natural formation processes. The Spitzer Space Telescope and other infrared instruments can detect thermal anomalies, which might hint at internal power sources or artificial heating systems. And with advanced imaging techniques, researchers examine surface textures, searching for manufacturing marks, geometric patterns, or structural elements that would suggest intelligent design rather than natural geological or impact processes. The predecessors. What lessons did scientists learn from previous mysterious objects that shaped current investigation protocols? The 2017 discovery of Oumuamua really changed the game for astronomers, establishing comprehensive analysis frameworks that are still in use today. Robert Warwick at the University of Hawaii was the first to detect Oumuamua, which showed unusual acceleration patterns that initially puzzled scientists, until natural explanations involving outgassing were confirmed. The controversy over Oumuamua's elongated shape and slight acceleration taught researchers the importance of gathering multiple types of observational data before jumping to conclusions. Avi Loeb from Harvard University suggested considering artificial origins for Oumuamua, which sparked important discussions about scientific methodology and the burden of proof needed for extraordinary claims. Then there was 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, which provided a more conventional example of an interstellar comet with clearly natural characteristics. These experiences established standard protocols for studying interstellar objects, like immediate spectroscopic analysis, trajectory monitoring, and international coordination for follow-up observations. Scientists learned to consider both natural and artificial explanations at the same time, while maintaining rigorous standards for evaluating evidence. The experiences with these objects also highlighted the need for rapid response capabilities, since interstellar visitors are only observable for limited time periods before they leave the solar system. Nowadays, modern protocols include automated alert systems that notify astronomers worldwide within just a few hours of discovery, enabling coordinated international observation campaigns to maximize data collection from these rare cosmic visitors. The cosmic journey. How do orbital mechanics help scientists distinguish between natural objects and potential alien spacecraft? Well, natural interstellar objects follow predictable trajectories determined by gravitational interactions with the sun and planets, while artificial objects might show unexplained course corrections or propulsion signatures. Gravitational physics gives us precise mathematical frameworks for calculating expected paths, allowing scientists to spot any deviations that could indicate active navigation systems. For example, the trajectory of 3I/Atlas follows a hyperbolic orbit with an eccentricity of 6.14, which is totally consistent with natural ejection from a distant star system millions of years ago. Scientists use sophisticated computer simulations to trace backward trajectories, trying to identify possible origin star systems and validate natural formation scenarios. Of course, unexpected acceleration or deceleration patterns might indicate propulsion systems, though natural phenomena like outgassing can also cause trajectory changes in comets and asteroids. JPL's navigation teams keep a close watch on object trajectories using radar and optical observations, measuring positions with extraordinary precision to catch even the subtlest motion anomalies. Artificial objects could show perfect geometric flight paths, precise timing and trajectory changes, or acceleration patterns that just don't fit with known natural forces like solar radiation pressure or gravitational slingshot effects. The Deep Space Network offers radar tracking capabilities that can pick up tiny changes in velocity or trajectory that optical telescopes might miss. Scientists also analyze how objects respond to solar radiation pressure, gravitational perturbations from planets, and other natural forces, just to make sure their motion follows purely physical laws, or to see if it hints at intelligent control systems managing their flight paths through the solar system. A scientific goldmine. What advanced technologies enable scientists to determine if mysterious objects are natural or artificial? Well, modern astronomical instruments provide, honestly, unprecedented capabilities for analyzing the physical properties and behavior of potential alien artifacts versus natural space debris. Spectroscopic analysis, using instruments like those on the James Webb Space Telescope, can identify specific chemical compositions, revealing whether objects contain materials consistent with natural formation or, unusual artificial alloys. High-resolution imaging from ground-based adaptive optic systems and space telescopes can resolve surface features as small as tens of meters, searching for geometric patterns, manufacturing marks, or structural elements that would indicate intelligent design. Radio astronomy facilities like the Very Large Array continuously monitor for electromagnetic emissions that might indicate communication systems, navigation equipment, or other technological signatures from mysterious objects. Infrared observations detect thermal signatures that could reveal internal power sources, artificial heating systems, or temperature regulation inconsistent with passive solar heating of natural materials. Advanced computer modeling allows scientists to simulate how various materials and structures would behave under different conditions, comparing observations with theoretical predictions for natural versus artificial objects. Gravitational wave detectors provide additional monitoring capabilities for massive objects that might employ, say, exotic propulsion systems. Machine learning algorithms process vast amounts of observational data, identifying subtle patterns and anomalies that might escape human analysis. And finally, international coordination through networks like the International Astronomical Union ensures that multiple independent teams analyze the same objects, reducing the risk of observational errors or biased interpretations that could lead to false conclusions about potential alien technology. Unanswered questions. What specific characteristics would definitively identify an object as alien technology rather than natural space debris? Scientists have established clear criteria for distinguishing artificial constructs from natural celestial objects, though, some borderline cases continue to challenge conventional analysis methods. Geometric precision in shape, surface features, or rotational periods would strongly suggest intelligent design, since natural processes rarely produce perfectly symmetrical or mathematically precise structures. Unusual material compositions containing pure metals, artificial alloys, or isotopic ratios inconsistent with stellar nucleosynthesis would indicate manufacturing rather than natural formation processes. Active electromagnetic emissions, especially coherent radio signals or structured data transmissions, would provide compelling evidence of technological origin and possibly intelligence. Propulsion signatures including unexplained acceleration, trajectory corrections, or energy emissions inconsistent with known natural forces would suggest artificial control systems. Surface features showing clear geometric patterns, construction joints, or manufacturing marks visible through high-resolution imaging would distinguish technology from natural geological processes. Internal structure revealed through radar or gravitational analysis might show artificial compartments, machinery, or organized systems rather than homogeneous natural composition. thermal anomalies indicating internal power sources, temperature regulation, or waste heat disposal would suggest active technological systems rather than passive solar heating. Response to external stimuli, such as changes in behavior when approached by spacecraft or exposed to radio signals, might indicate artificial intelligence or automated systems. The SETI Institute maintains protocols for evaluating potential techno-signatures, requiring multiple independent confirmations before announcing discoveries of artificial objects. Scientists continue refining detection methods and analysis techniques to ensure they can recognize genuine alien technology while, avoiding false positives from natural phenomena. The alien question. How do scientists balance open-minded investigation with rigorous skepticism when evaluating potential alien artifacts? The scientific method requires maintaining both receptivity to extraordinary discoveries and strict evidential standards that prevent premature conclusions about alien technology. Avi Loeb, chair of Harvard's astronomy department, advocates for seriously considering artificial origins when natural explanations prove inadequate, while emphasizing the need for extraordinary evidence to support extraordinary claims. Carl Sagan's famous principle that extraordinary claims require extraordinary evidence guides most astronomical investigations, ensuring that potential alien discoveries undergo the most rigorous peer review and verification processes. Scientists recognize that discovering genuine alien technology would represent one of humanity's most significant achievements, requiring absolute certainty to avoid false announcements that could damage scientific credibility. The SETI Institute has developed comprehensive protocols for evaluating potential techno-signatures, including multiple independent verification requirements and international coordination before making public announcements. Natural explanations must be thoroughly explored and eliminated before considering artificial origins, as the history of astronomy shows that apparently anomalous objects often have conventional explanations discovered through continued observation. Peer review processes ensure that multiple independent scientists analyze the same data and observations, reducing the risk of individual bias or analytical errors that might lead to incorrect conclusions. The scientific community maintains healthy skepticism while remaining genuinely open to discovering evidence of alien technology, balancing the need for rigorous investigation with the recognition that such discoveries would profoundly impact human understanding of our place in the universe and the prevalence of intelligent life throughout the galaxy. Dawn of a new era. What does the future hold for detecting and analyzing potentially artificial objects in our solar system? Technological advances in astronomy continue revolutionizing our ability to identify, track, and study mysterious visitors that might represent alien technology rather than natural space debris. Next-generation telescopes like the Vera Rubin Observatory will survey the entire visible sky nightly, dramatically increasing discovery rates for interstellar objects and providing rapid alerts for international follow-up observations. Advanced artificial intelligence systems will analyze observational data in real time, identifying subtle anomalies and patterns that might escape human attention, while flagging objects requiring immediate investigation. Space-based observation platforms will provide continuous monitoring capabilities without atmospheric interference, enabling detailed spectroscopic and thermal analysis of potentially artificial objects throughout their solar system passages. Improved international coordination through organizations like the International Astronomical Union ensures rapid information sharing and coordinated observation campaigns that maximize data collection from rare interstellar visitors. Radar astronomy facilities continue expanding their capabilities for detailed trajectory tracking and surface mapping, providing unprecedented precision in detecting artificial structures or unexpected motion patterns. Future space missions might include dedicated interceptor spacecraft designed to rendezvous with mysterious objects for close-range analysis, collecting samples and detailed measurements impossible from ground-based observations. The Breakthrough Listen project and similar initiatives continue expanding radio monitoring capabilities, searching for electromagnetic signatures that might indicate technological origins. Enhanced computer modeling and simulation capabilities will enable more sophisticated analysis of observational data, comparing observations with theoretical predictions for both natural and artificial objects to distinguish between conventional explanations and genuinely anomalous discoveries requiring extraordinary investigation. The search for alien technology requires balancing scientific rigor with open-minded investigation, ensuring we don't miss genuine discoveries while avoiding false alarms. As our detection capabilities advance, astronomers remain vigilant for objects that might represent humanity's first contact with extraterrestrial intelligence. Every mysterious visitor gets the same careful analysis, protecting both scientific credibility and our readiness for extraordinary discoveries. Keep exploring the cosmos with Simply Science. Like, share, and subscribe for more fascinating insights into our universe's greatest mysteries. Did you know that every time you breathe, you're inhaling atoms that were once inside the lungs of Julius Caesar, Einstein, and every person who ever lived? The human body completely replaces itself every 7 years, yet somehow you remain you. Same memories, same personality, same consciousness. Here's the mind-bending truth. You're literally not the same person you were a decade ago, down to the atomic level. But wait until you hear what scientists just discovered about consciousness itself. Do you know what happens to yourself during those 7 years of complete cellular replacement? The Large Hadron Collider Monster. Deep underground, stretching across the border between France and Switzerland, lies humanity's most ambitious and terrifying scientific achievement. The Large Hadron Collider isn't just big, it's monumentally massive, forming a perfect 27-kilometer ring that could swallow entire cities. This isn't your high school physics lab. We're talking about a machine so powerful it accelerates protons to 99.9999991% the speed of light before smashing them together with the force of 2 freight trains colliding head-on. The energy released in these collisions is so intense it recreates conditions that existed just moments after the Big Bang itself. Think about that for a second. Scientists are literally recreating the birth of the universe in an underground tunnel. The superconducting magnets alone are colder than outer space, chilled to -271 degrees Celsius using liquid helium. When this beast fires up, it consumes enough electricity to power a small country. The collision points generate temperatures 100,000 times hotter than the core of the sun. This is where the magic happens, where ordinary matter gets obliterated and the fundamental building blocks of reality reveal their deepest secrets. Every second, billions of particles are destroyed and created in an endless cycle of cosmic violence that pushes the boundaries of what's physically possible. The black hole theory bombshell. When theoretical physicists first suggested that CERN's particle collisions might actually spawn microscopic black holes, the scientific community didn't just raise eyebrows, they collectively held their breath. This wasn't some wild science fiction fantasy dreamed up by Hollywood writers. We're talking about legitimate Nobel Prize-winning scientists publishing peer-reviewed papers, claiming that when you slam protons together with enough raw energy, space-time itself might collapse into infinitesimally small gravitational monsters. These aren't the massive stellar black holes that devour entire solar systems. We're talking about quantum-scale vortexes smaller than a single atom, existing for less than a trillionth of a second. But here's the absolutely mind-bending part. Even though they're microscopic, they still possess the fundamental properties of their cosmic cousins. They warp space-time, bend light, and theoretically could interact with dimensions we can't even perceive. The mathematics behind this theory are so complex that only a handful of physicists on Earth truly understand the implications. What makes this even more incredible is that these micro-black holes wouldn't behave like anything we've ever observed in nature. They'd be born, live their entire existence, and die in a time span so brief that light itself couldn't travel the width of a proton. Yet in that impossibly short moment, they might unlock secrets about the fundamental structure of reality that have puzzled humanity for centuries. The Hawking radiation discovery. Back in 1974, Stephen Hawking made a discovery that left the entire scientific world speechless, and fundamentally changed how we understand black holes forever. He proved that these cosmic monsters aren't actually black at all. They're slowly bleeding energy back into the universe through a process so counterintuitive, it sounds like pure magic. Here's the mind-bending part. The smaller a black hole gets, the hotter it becomes and the faster it evaporates. It's like cosmic irony. The tiniest black holes burn the brightest before vanishing completely. Hawking realized that, at the quantum level, pairs of particles constantly pop into existence right at the edge of a black hole's event horizon. Normally, these particle pairs would annihilate each other instantly, but the black hole's immense gravity tears them apart. One particle falls into the black hole while its partner escapes as radiation slowly stealing the black hole's mass and energy. This means every black hole in the universe is essentially a ticking time bomb destined to evaporate completely given enough time. For the microscopic black holes potentially created at CERN, this process happens almost instantaneously. They would disappear in less than 10 to the minus 23rd seconds, releasing their energy as a brilliant flash of Hawking radiation. This discovery didn't just explain how black holes die, it revealed that the universe has a built-in safety mechanism preventing these quantum monsters from growing out of control. The dimensional portal possibility. The most mind-blowing theory surrounding CERN's potential black hole creation isn't just about the holes themselves, it's about where they might lead. According to cutting-edge string theory, our universe isn't the flat, three-dimensional space we experience every day. Instead, we're living on a thin slice of reality floating in a vast ocean of hidden dimensions that exist parallel to our own. These extra dimensions are so tightly curled up that they're invisible to us, but they're there, influencing everything from the fundamental forces to the very fabric of space-time itself. When CERN smashes particles together with enough energy to potentially create micro-black holes, these quantum tunnels might actually punch temporary holes through the barriers separating our dimension from these hidden realms. This could explain one of physics' greatest mysteries, why gravity is trillions of times weaker than electromagnetic forces. The theory suggests that gravity isn't actually weak, it's just spreading its influence across multiple dimensions simultaneously, diluting its strength in our three-dimensional slice of reality. If micro-black holes at CERN really are acting as brief portals to these extra dimensions, then every collision isn't just creating and destroying matter, it's opening fleeting windows into parallel universes that exist mere millimeters away from us in directions we can't even comprehend. This means CERN might not just be studying particles, it could be humanity's first glimpse into the true multidimensional nature of existence itself. The safety panic that followed. When word leaked that CERN scientists were theoretically capable of creating microscopic black holes, the public reaction was nothing short of apocalyptic hysteria. Overnight, conspiracy theories flooded social media claiming that physicists were about to accidentally destroy Earth by creating an unstoppable gravitational monster that would devour the planet from the inside out. The panic reached such fever pitch that multiple lawsuits were filed in courts across Europe and America, with terrified citizens demanding immediate injunctions to halt the Large Hadron Collider's operations. News outlets sensationalized the story with headlines screaming about scientists playing God and the end of the world, hidden beneath Switzerland. Online forums exploded with amateur physicists and concerned parents sharing viral videos, explaining how a single microscopic black hole could theoretically grow by consuming surrounding matter until it swallowed the entire solar system. The fear wasn't entirely irrational. After all, we're talking about recreating one of the universe's most destructive phenomena in a laboratory setting. Protesters gathered outside CERN facilities holding signs reading, "Stop the Doomsday Machine," while petition websites crashed from millions of signatures demanding the project's cancellation. Religious groups declared it an affront to divine creation, while survivalists began stockpiling supplies for the impending apocalypse. The scientific community found themselves in the unprecedented position of having to calm global panic, while simultaneously pushing forward with experiments that could revolutionize our understanding of reality itself. The cosmic ray reality check. While panicked crowds demanded CERN's shutdown, physicists delivered the most elegant scientific smackdown in history by simply pointing upward at the sky. Every single second of every single day, our planet gets bombarded by cosmic rays, high-energy particles from deep space that crash into Earth's atmosphere with energies that make CERN's collisions look like gentle bumper cars at a carnival. These cosmic bullets have been pummeling our planet for over 4.5 billion years, generating particle collisions with energies thousands of times more powerful than anything the Large Hadron Collider could ever produce. If dangerous, Earth-devouring black holes were actually possible at these energy levels, our planet would have been consumed eons before the first dinosaur ever walked the Earth. The Moon, with no protective atmosphere, takes these cosmic ray hits directly on its surface, yet it's still hanging peacefully in our sky after billions of years of constant bombardment. Scientists calculated that cosmic rays create the equivalent of millions of CERN-level collisions in our atmosphere every single day, and we're all still here. completely unharmed. This cosmic ray argument became the ultimate reality check that silenced most critics. Nature has been running the exact same experiment CERN was proposing, but on a vastly larger scale for literally billions of years. The universe itself had already proven that these high-energy collisions were completely safe, making the doomsday fears seem almost comically overblown. The actual experimental results. When the Large Hadron Collider roared to life for its first high-energy collisions, the entire scientific world held its breath as detectors captured data from the most violent particle crashes in human history. What happened next wasn't the apocalyptic black hole scenario that terrified millions. No, it was something far more extraordinary. The collisions revealed a hidden universe of subatomic particles that had been theoretical fantasies for decades, suddenly becoming measurable reality. Scientists watched in awe as their detectors registered the creation and immediate decay of exotic particles with names like strange quarks, charm quarks, and bottom quarks. Building blocks of matter so fundamental they only exist for microseconds before transforming into other particles. The most groundbreaking discovery came in 2012 when they finally detected the Higgs boson, the so-called God particle that gives all other particles their mass. This wasn't just a scientific victory, it was confirmation that our mathematical models of the universe were actually correct. Each collision produced cascades of data showing how matter behaves at the most fundamental level, revealing that the universe operates according to principles so elegant and precise, they border on the miraculous. Instead of creating world-ending black holes, CERN was uncovering the deepest secrets of existence itself, proving that sometimes the most terrifying experiments lead to the most beautiful discoveries about the nature of reality. The missing energy mystery. The most spine-tingling discovery at CERN wasn't what scientists found, it was what they couldn't find. During certain high-energy particle collisions, detectors registered something that honestly should have been impossible according to our understanding of physics. Energy was disappearing without a trace. Not just small amounts, but significant chunks of energy that should have been conserved according to the fundamental laws of the universe. Every collision should follow the ironclad rule that energy can neither be created nor destroyed, only transformed from one form to another. Yet here were collisions where the energy going in was measurably greater than the energy coming out, as if some invisible force was stealing it mid-collision. The missing energy wasn't random, it followed specific patterns that sent theoretical physicists into overdrive. The leading explanation is so mind-bending it sounds like science fiction. The energy is leaking into parallel dimensions through microscopic tears in space-time created during the most violent collisions. If this theory is correct, then CERN isn't just smashing particles together, it's accidentally punching holes between our universe and hidden dimensions that exist alongside our own reality. Each missing joule of energy could be proof that our three-dimensional world is just one layer of a vast multi-dimensional cosmos. This means every time energy vanishes at CERN, we might be witnessing the first direct evidence that parallel universes aren't just theoretical concepts, but actual places where our energy is escaping to through quantum tunnels we're only beginning to understand. The future implications. The potential ability to create and study quantum black holes at CERN represents far more than just another scientific achievement. It could be the key that unlocks technologies so advanced they would make our current civilization look, well, primitive by comparison. If scientists can reliably generate these microscopic gravitational anomalies, we're not just talking about understanding physics better, we're talking about harnessing the fundamental forces that govern reality itself. These quantum black holes could become the ultimate energy source, converting matter directly into pure energy with 100% efficiency, making nuclear power look like a candle compared to the sun. The implications for space travel are staggering. Imagine propulsion systems that manipulate space-time itself, allowing spacecraft to bend the fabric of reality and travel vast distances in impossibly short time frames. Even more mind-bending is the possibility of using controlled micro-black holes to access parallel dimensions, potentially opening doorways to alternate versions of our universe where the laws of physics might operate differently. The technology could revolutionize computing by creating quantum processors that operate across multiple dimensions simultaneously, solving problems that would take conventional computers millions of years to crack. We might even develop the ability to manipulate time itself, using the extreme gravitational fields of micro-black holes to create localized time dilation effects. This isn't science fiction anymore. It's the logical next step in human technological evolution, where we transition from merely observing the universe to actively reshaping it according to our will. The ongoing research. At this very moment, teams of physicists around the world are sifting through petabytes of collision data from CERN, searching for the telltale signatures of microscopic black holes that could rewrite our understanding of existence itself. Every single collision generates thousands of data points that must be meticulously analyzed by both human researchers and artificial intelligence systems designed specifically to detect anomalies that human eyes might miss. The search isn't random. Scientists know exactly what to look for: specific patterns of missing energy, unusual particle decay signatures, and gravitational effects that last for impossibly brief moments before vanishing completely. Advanced algorithms run 24/7, comparing actual collision results against theoretical predictions, flagging any events that deviate from expected outcomes. The most promising candidates undergo intense scrutiny, with teams of experts examining every microsecond of data to determine whether they've witnessed the birth and death of a quantum black hole. Recent upgrades to CERN's detection systems have increased sensitivity by orders of magnitude, allowing researchers to probe deeper into the quantum realm than ever before. Each new collision brings humanity closer to answering fundamental questions about the nature of reality. Are extra dimensions real? Can we create controlled tiers in space-time? Do parallel universes actually exist just beyond our perception? The answers to these questions aren't just academic curiosities. They could fundamentally transform our species' relationship with the cosmos and unlock technologies that seem impossible today. So there you have it. CERN might be creating microscopic black holes that could unlock the secrets of parallel dimensions and reshape our understanding of reality itself. The universe is far stranger and more incredible than we ever imagined. What's your take on this? Are we playing with forces beyond our control, or are we on the verge of the greatest scientific breakthrough in human history? Drop your thoughts in the comments below. I read every single one and love hearing your perspectives. If this blew your mind like it did mine, smash that subscribe button and hit the bell icon so you never miss our latest mind-bending science content. This is Simply Science, and I'll see you in the next video.